Hi, welcome to another edition of Calculus 3. Today we are going to continue our conversation about gradient and its applications. We were talking about tangent planes and normal lines, and today we are going to look at the last two on our list of applications. So you remember we had 6 problems slated for ourselves as applications of gradient. We went through the item number 1, which was finding equation of tangent plane, finding equation of normal line, finding equation of tangent line to the intersection of two surfaces, finding inclination angle of tangent plane, about which I'm going to add an additional formula today. And then two major items for today: finding points on a surface where the tangent plane is horizontal. Okay, we said this is a standard topic we had in Calculus 1, where you were finding the high and low points of a function at which the tangent line is horizontal. Now we are going after tangent plane being horizontal. And then last item, angle between two surfaces. Just same way that we can talk about the angle between two lines or two curves, we can also talk about the angle between two surfaces. Let's go ahead and start this topic. Before we do that, let me just paraphrase something we did last time on inclination angle before we start today. So for the inclination angle, we said traditionally they ask for an acute angle, in which case you have to make some modification. Here is a clean-cut formula that incorporates that and always gives you an acute angle. The inclination angle is arc cosine of f sub z divided by norm of the gradient. Okay, so let's start our lecture. So we said we want to find the points on a surface where tangent plane find points on a surface where tangent plane is horizontal. Well, we said in Calculus 1 we had some function and we are looking for highs and lows of it, and that brought us to the issue of where the function becomes stationary, where the tangent line, if it exists, is horizontal. Well, that was where the derivative was 0 for the high and the low, and sometimes you run into the issue that, well, it's neither high or low, but the tangent line is horizontal. So we had all these topics faced for simple functions in Calculus 1. Exact same thing comes up in Calculus 3. So suppose I have a function, say x squared plus y squared plus z squared, say 8x minus 4y plus 2z, say equal to 100. That's what we want. Find the points on this thing where the surface, where the tangent plane is horizontal. Well, we are going to do this thing two ways. One style is what you would have done actually in high school, long before you entered calculus. You could have done that with just your college algebra, because this is a simple function. And then we can also come back and say that, well, in Calculus 3, for more complicated functions, what would we do? Let's do the Calculus 3 style first. So Calculus 3 style, well, if you have a surface, we said its normal is along gradient of the function that defines that surface. Like if your surface is given by level surface of a function f equal to 0, then gradient of the function is going to be normal to it. So if you want the tangent plane to be horizontal, well, the normal to it will have 0 component 1, 0 component 2, and the third component, which is your non-zero component there. So you need the first two to be 0, so that means that you need f sub x to be 0 and f sub y to be 0. So what we do first is that we define our function f. It's nice to bring everything to one side, so if there are two sides of equation, we bring everything to one side. So that is my function f. I go ahead and calculate its gradient. I need fx, fy. In this case, I don't really need fz. I just want to make sure it is not 0. Fx is what? Is 2x plus 8. And that has to be 0. Fy is 2y minus 4. And that one has to be 0. So this tells me that x has to be minus 4. And so y has to be equal to 2. As simple as that. Our problem is actually 90% done. This is x, y coordinates of a plane, a point where the tangent plane will be horizontal. So fx equal to 0, fy equal to 0. Over there you had just f prime equal to 0. You just have to do two of them. Well, what if they want also z? How about z? What is z? Easy way, just plug these things back in your equation. You remember this was f equal to 0, or the original equation. Plug x minus 4, y equal to 2 into that. So what do I have? Minus 4 squared plus 2 squared plus z squared plus 8 times minus 4 times 2 and 2z minus 100, that's equal to 0. So 16 and 4 and z squared minus 32 minus 8 plus 2z minus 100 equal to 0. So let's clean this up. I have z squared. Let's write that first, and then I have a 2z, and then let's add up all the positives. So what do I have? 16 and 4. I have 20, and then minus 140, so it looks like a total of minus 120 equal to 0. Well, how do you factor that? Two numbers such that the sum is 2 and the product is minus 120. What's that? 12 and minus 10. So I get two answers. Z is equal to 12, z is equal to, minus 12, and z is equal to 10. So here are my two answers. I have 10 and I have minus 12. At these two locations, tangent plane is going to be horizontal. So tangent plane let's write it with parentheses so it doesn't get point at this point and at the point minus 4 and 2 and that was 10, 10 and minus 12. Okay, well, we said you could have done this thing back in high school. How would you do that? When you look at this thing, you realize this looks a lot like the equation of the circle we had back then. Well, this is x, y, and z, so it's going to be equation of a sphere. So a sphere is going to have a high, if you have a sphere in your x, y coordinate system, well, there's going to be a high point and a low point, and at these 2 points we are going to have tangent planes that are horizontal. Well, how do we do that without the advanced notion of gradients and such? Well, we write the equation of a sphere. Exact same way we wrote the equation of a circle. So I put my x's together, so calculus 3, and this would be pre-cal style for the same thing, 8x. Then I separate my y's, y squared minus 4y, and I separate my z's, so z squared plus 2z, and I put my other number here, 100. So we say, what do I need to complete this? Can you find for me? So here's a bit of a participation for you. What do I do there? What is missing to make it a complete square? So of course I need a 16 here, half of this squared, half of this squared, half of this squared. Whatever you add to one side, you add to the other side. What does this do? Well, you have the completed square, x plus 4 squared plus y minus 2 squared, z plus 1 squared, and we are lucky that on the other side it's also a square, 121. Isn't that peculiar? So that is, what's that? That's a sphere. Where's the center of the sphere? Center is where these parentheses become 0, minus 4 and 2 and minus 1. What's the radius of it? Radius, of course, square root of that, 11. So this is the x, y, z of the center. If I start at this center and go 11 points up, so if I do minus 1 plus 11, I get to 10. That is, of course, exactly that. You go as much as, so if I start at the center and go straight up as much as the radius, of course I'm going to reach the highest point. And then same way, if I start at minus 1 and come down by that much, I get to minus 12, and minus 12 is going to be this one. That's my minus 12, and this is my 10 up here. Well, that was simple. So let's see calculus 3 version. You clean up your equations. Derivative with respect to x and y are taken of the equation, and then we solve the resulting equation, find the x, y, and z, and we're done. If the problem was so simple that it would be just completion of squares, it's our lucky day, and we can do it that way too. Let's go ahead and quickly take a look at okay, so I have written the equation of a sphere here. That's an implicit equation, so that's my sphere. So you notice my x, y, and the z up here. This is going to be a high point of it. Okay, this is the high point. The tangent plane is horizontal. Horizontal would make it perpendicular to z-axis. At the bottom we have z equal to minus 12. So this is the bottom of this, that's the top of it, and well, any other function would have been same. Okay, that was simple and quick. Let's move on to another application, which was the issue of the angle between surfaces. So let's go quickly go through this thing. First of all, how do you define an angle? You have two vectors, let's call them A and B, and there's an angle between the two of them. Let's start with that way back when we just talk about angles. Well, how do you find that? We said one convenient way in calculus is to use a dot product. A dot B was A dot B, length of A times length of B times cosine of the angle. So if you want the angle, you rearrange this thing, A dot B, and if you want the angle, you'll use arc cosine of A dot B, and then we said well, when you are talking about angles, there are always two angles you can sometimes there are two angles to go after when you are talking about, say, two lines. When you have vectors, well, there's just one definition for this, but when you have two lines, you can choose that as your angle, or you can choose that one as your angle, and the two of them are complementary. In most circumstances, people go after the acute angle. If you want the acute, so if you insist on acute theta, you turn this thing into a positive, so you force it positive, and then so you don't have to deal with obtuse angles. Okay, now suppose you had two curves. Suppose I have a curve here and another curve here. Let's draw it better. Okay, how do we define this? The angle between these two. Well, we go ahead and draw tangent line of this one and the tangent line of the other one, and the angle between those two tangent lines will be defined as the angle between the two curves. And for these lines, we just use the tools that we had here. And when the question comes out, well, how do you figure out a vector that is lining up with them? A convenient way of handling this is to go ahead and take a look at the normal to the two surfaces, or the normal to the two tangent planes. So I draw a vector perpendicular to the first one and another vector perpendicular to the second one. B. So if you are interested in this angle between the two curves, that's the same as the angle between the normals of the two curves. And how do you get the normals? Well, that's where our friend comes in. You get the gradient gives you the normal, that's a vector, and then you find the angle between those two vectors, and then you are all set. Okay, so we have two surfaces. So exact same thing applies in the case of surfaces. Let me go and show a picture so that we know what we're talking about. Let's go to our trusted software here. We have okay, now I have drawn two planes. We can talk about the angle between these two planes, just like when you take a book and you open it up, one page of the book, or the side of the book that you open, the cover that you open, makes an angle with the rest of the book, and we want to figure out how to find that. Easiest way to do this is by using the normal to the planes. So instead of using the plane itself, we actually use the normal. So if you add these two, like the two sides of a plane, here is the normal number 1 to the red one, and is the normal number 2 to the yellow one. We measure the angle between the two normals. That's the most convenient way of handling the situation. So if you have two surfaces, first you get the tangent planes, then you get the normals to the tangent planes, and then you find the angle between the two of them. So in practice, actually, it's a very simple task. Let's go ahead and take an example. Suppose I have two surfaces. So it says, so find angle between x squared plus say 2y squared plus say 3z squared is equal to 3, and another surface. So we have two surfaces now, x squared plus y squared plus z squared, 6x minus 10y, 14, is that just 14? um, let me make sure that yeah, it's just there's no z in it, it's just a 14 equal to 0. That's all. We want to find the angle between these two. So these are two surfaces. Again, before we go any deeper in this issue, do you remember what these two surfaces are? Surface number 2, that should be very familiar to you right now. We just did it, is that right? What is it? That is a sphere, of course. This one, from the very first lecture of the semester, remember what kind of a creature that one is? That is an ellipsoid. So long as these numbers are different, positive, it's just an ellipsoid. So we have two surfaces, one a bit more familiar to us than the other one. When the question is find the angle, you have to give a location at which you are interested in at that angle. As you go around, that angle is going to change. Different points, you get different type of answer. So here they give you at the point, let's call it P0. P0 is -1, 1, 0. First, let's go ahead and make sure we understand that this has to be on both of them, that is on the intersection. So if I put -1 and a 1 here, I do get 3. So this point P0 is on this surface. And how about here? So if I put 1 plus 1 plus 0 plus 6 minus well, that was, excuse me, -6, -10, and 14. So what is that? -2 plus 2 is equal to 0. So since the two sides agree, that means the point is actually on the surface. So this point is on both of these surfaces. Now we go ahead and find out the angle between the two surfaces. Let's call this thing F, call this one G, and to make it a function, let me go ahead and say -3 equal to 0. And so F is this function and G is this function. I go ahead and calculate gradient of F. So that's going to be the normal to F, for example, like this blue vector here. So who is that? The 2x, 4y, 6z. At P0, our gradient becomes so -1, this makes it -2, and then 4 and 0. Gradient of G, 2x plus 6. Okay, derivative with respect to x, that is 2x plus 6. Derivative with respect to y, that's 2y minus 10. Derivative with respect to z, that's just 2z. At P0, again, I'm hunting for this other vector. My gradient of G becomes, okay, let's put the numbers. I have this is x is -1, and I put it here, I get a 4. And y is 1, so that makes it -8. And z is still 0. So I have two vectors. To simplify, vector 1 is -2, 4, 0. Clean up. Number 2 is 4, -8, and 0. So the angle is going to be, or at least acute angle, would be arc cosine of A dot B, force it positive, over the length of A times length of B. Okay, we can calculate this thing and figure out what that is, but before doing that, maybe if you look at this, it will scream at us as to what the answer is. What is the deal with A and B? If this is A, so happens this B is exactly -4 times A, so B is going like this. So the angle between the two of them, well, in geometry you say it's pi, but if you look at the acute angle, like if you consider two lines, one line is going like this, so you have maybe one line is like this and another line is like that. The angle between these two lines, you can say it's 0, you can say it's pi. Either way you are going to be correct, and we are going with the acute angle, so we say angle is 0. But in general, what do you do? In general, you say arc cosine of a cross b, a dot b, so it becomes minus 8. So I have minus 8 minus 32 over, so I have to force this thing positive, 2 squared plus 4 squared, and 4 squared plus 8 squared, so that's going to be arc cosine of 40 over, this is square root of 20, this one is square root of what's that, 16 and 64, that is going to be 16 and 64, so this is going to be 80. So simplifying that, it becomes arc cosine of 40 multiply it makes 1600, it becomes arc cosine of 40 over 40, and that's equal to arc cosine of, well, that's 1. What's an angle whose cosine is 1? After a lot of zigzag, we come to 0, which is just what we saw here. If you hadn't put the absolute value, this would have been arc cosine of -1, and you get a pi in that case. They are really both correct, but your textbook typically goes with acute angle. Okay, what's the when you say angle is 0 or angle is pi, what does that mean? Can you think about what word do you use to describe situations where the angle between two surfaces is 0? What does that mean? So think about it for a second, and then I'll show you the picture. So you pause this thing. Okay, it looks like we have to build it from scratch. Let me go to this website again. Well, it's not cooperating with us. Let's go ahead and do it here. I have to so we have two surfaces to make. They are both implicit surfaces, meaning x, y, z are both on one side, so I use implicit. One of the equation was 2, and this one was 3, and the right hand side was 3 again. Okay, it's warning about a typo. Let's correct that. Okay, so we have a surface here, x squared, oh, it was 2y squared. A bit different, so okay, so that is kind of a football shaped thing, and then the other one was a sphere, so that's also implicit. So implicit, we're gonna come here and x squared plus y squared plus z squared. It writes some default formula for you, and then you change it. 6x, we had minus 10y, and then I had plus 14, and it was all equal to 0. Okay. Well, you see a piece of it, meaning we have to change our axis to see the rest of it. In fact, this is part of a big sphere. Well, all we want to see is that what happens between the two of them, and what happens is that they are barely touching each other and moving away. Means these two surfaces are tangent to each other. Okay, so the description of a tangent is like two balls that are coming and touching each other. So two marbles, or one ping pong ball and another marble or something, or two billiard balls or something. So they are, at this point, they are tangent to each other. The meaning of that is that their tangent planes will be the same. Okay, the meaning of that is the tangent plane is the same. So in simple problems, the angle turns out to be either 0, which means they are tangent, or turns out to be 90, which means these two surfaces are perpendicular to each other. That's another favorite situation, but of course the angle could be any number. Okay, so we have, let's go back to what was it that we did. We covered all the bases of what we promised to do. We thankfully we did all of these. So we did tangent plane where it's horizontal, and angle between two surfaces. Now, finding maximum minimum is going to be an extensive topic all by itself. It has to be handled in some separate lectures, just like in Calculus 1 you had extensive number of lectures on maximum minimum. So finding extremum points of a surface is by itself a chapter. So let's stop here and meet again for continuation of topics of interest. Until next time, good luck and God bless.